Great, we're live. Welcome everyone for this panel on reproducibility crisis in AI, lessons learned from other fields. And it's a pleasure to be joined today by three esteemed panelists who will have a conversation today with us about this topic. They very much come from different fields, and we can have a conversation which we learn from other fields that may be ahead on the question of reproducibility in science for learning analytics and for education, and see what notes we can share. And so it is wonderful to be joined today by Tim Errington from the Center for Open Science, by Benjamin Haibe-Kains, I hope I got that right, from the University of Toronto, and by Chris Brooks from the University of Michigan. Today, the topic is reproducibility, but we'll also be talking about some related concepts, such as replicability, as well as transparency, and how to align incentives in a scientific community in order to encourage scientists to strive towards these goals. We have seen a lot of different attempts over the last few years in order to set the right incentives. And so I look forward to a great conversation with our three panelists on the ideas that have been tested, what they can share about what works well, and where we still have room to grow. I especially rely on Chris Brooks to relate some of these questions to the education space, where he's a local expert on that topic, and to learn a lot from both Tim and Benjamin about sort of the broader space of reproducibility, and especially in the case of medicine. So without further ado, I will encourage you to post your questions throughout, both in Zoom right here or on Hoover in the question forum. We'll have time for questions at the end. For the last half hour, we'll give each of the panelists 10 minutes to present some of their ideas, and then we'll have time to discuss and bring in your questions. So first off, we will have a presentation by Tim Errington, and Tim is the Director of Research at the Center for Open Science, which is located in Charlottesville, Virginia. He is one of the co-authors of a very much cited piece that stirred up a lot of attention about the reproducibility of psychological science. His work at COS focuses on increasing reproducibility and openness of scientific research. And he, as I mentioned before, has a background in the medical area, or the biology, specifically a PhD in microbiology, immunology, and cancer biology from the University of Virginia. Tim, thank you for joining us, and the floor is yours.
Great, thank you for the invitation and for kicking us off. All right, so I'm going to share my screen here. Should be good, it looks like. So I'm from the Center for Open Science. We're a nonprofit, and today, in the 10 minutes I get, I want to talk a little bit about the reproducibility challenges. I'm going to use that word broadly at first, then I'll define what I mean by it in a little bit. But kind of also framing it a little bit about like how do we know what we know and what can we learn from it. I'm going to talk about it in the context of two projects that you just heard about, too, psychology and my primary background, preclinical cancer biology. And also, just in case people want it, these slides are publicly available too at that link. Okay, so before getting into those projects, I want to frame it in a larger sense, which is the system, the incentive system, at least the way that we think about it at the Center for Open Science. And if we think about credible research, right, the enterprise that we have for credible research, it looks something like this, right, where we have these incentives for rigor, reproducibility, again, using those terms broadly. And this leads to these downstream aspects, right, where we report everything, we have replication studies or reproducibility studies, we're very transparent, rigorous, and we have highly credible research that's very trustworthy and a good return on investment. This is what we're all aiming for. But the question is this actually how our incentives are aligned? So I'm going to tell you kind of, I think, what's really happening, right? Which is our incentives are not for what I just told you. Our incentives are for novel, positive, tidy outcomes, right? That's what we publish. That's kind of what we end up showing and communicating to each other largely. And then that means that we're actually not doing the practices I showed you before that you end up having, more likely unknowingly, but also knowingly in some cases, selective reporting, questionable research practices, not all the sharing and transparency that we strive for, and not a lot of replications or reproductions occurring, right? So new evidence testing the same thing. That also means then that the research we have is not as credible as we think it is. We have to sift through it. And that also means that we're not really allowing that self-corrective process to occur, something that we know is vital to the research ecosystem. And in the end, instead of credible research, we actually have what is more like incredible research. And it's not having the credibility that we want. It's slowing our progress, and we're not really getting that return of investment that we were hoping for. So again, painting this kind of in a bit of a stance, because I think these are the aspects downstream from the incentives that really are what we need to be able to attend to, kind of aligning what we want with those incentives and the processes that fit. So let me give you an example of kind of where these types of aspects kind of come through. I'm going to give you a walkthrough of one of these projects. Let me give you the motivation for it. And this is, again, in my space. I'm going to start with this project in preclinical cancer biology. So the concerns that were raised in this field came actually from the pharmaceutical industry. Back in the early 2012, 2011, there were these two white papers. These are good examples that were published by some authors from Bayer and Amgen, two large pharmaceutical companies, basically saying that when they look back at research that they use that are being published largely in the academic space, they have a hard time building on it, replicating, right, translating. What was important, though, is that these are white papers. They didn't really get into the details. In fact, these are the only two bits in these two statements that really kind of discuss what they were doing, right? So the terminology is vague, and the data and the methods are vague. But nonetheless, right, the alarms have been raised that there's something going on, that maybe the research is more incredible and not as credible as we hoped for. So I spent at the Center for Open Science, we spent about 8 years, and we just finished up a project that was looking at, well, whether these claims, these statements have some truth to them, and also trying to be more transparent in our own process. So what we finished last year, started in 2013, was doing a project looking at the replicability of preclinical cancer research. So here it's saying, I'm going to redo the experiment again, collect new data that's done the same way as the originals, and see, after analyzing it, if I can get similar evidence. When we did this project, we did it from a systematic standpoint, just kind of sampling high impact preclinical cancer biology papers, but we did everything in the open, right? We were trying to make our process, our data, all the code and materials openly available. We also introduced a concept, which is, instead of just running and doing kind of status quo, trying to redo the exact same experiment, collecting new data the same way, analyzing it the same way to see if we get similar results. Instead, we introduced this concept of pre-commitment, which is, in here, we were doing it in concert with a journal, eLife. And this concept is called registered reports, where the protocols, our methodology, how we're going to collect the data, how we're going to analyze the data, was done beforehand. So we submitted to the journal our protocols and our analytical plans. And the journals and the researchers ourselves, reviewers, editors, all committed to that design after it went through peer review. So after revise, resubmit. And only after that did we then conduct the research. The nice thing about that method is also the journal eLife committed to publishing those outcomes regardless of what we found, positive or negative, as long as we adhered to those pre-commitments, as long as our controls worked, and as long as we were sharing everything. So I'm going over this pretty fast, but you can find more project info at that link if you want to. But I wanted to introduce this concept of pre-commitment, pre-registration registry reports. There's a lot of different names for it. Well, what did we find? Well, the first thing is we found that it was challenging. So this is actually what I think is right off the bat one of the issues that we've had. And I'm just giving you this as an example from this discipline. You see it in other ones, which is there's not a lot of transparency and access to information. So for example, in this project, of all the experiments we were looking at, only 2% had data that was open. And then even after talking to the authors to try to request the raw data, only 16% were able to give that to us. Some didn't want to, some couldn't. They didn't have access to it anymore after they published the results. And this is just a couple years after publishing. We couldn't design the protocols to collect data again by ourselves, right? It was not enough methodology was actually in the paper. Not even the reagents, the materials that we use to conduct the experiments, in this case, like animal models or cell lines, the type of research this was looking at. Even though about 3/4 said that they would share. Only a third ultimately did as well. And what that really gets at is assistance, help with protocol, help with this entire process, which is it's very much bimodal. We had about a quarter that were incredibly helpful, trying to help us figure out all the details that were not readily available in the paper. But about a third would not help us, either wouldn't respond or would not actively support us. So these are the types of challenges that actually hurt with reproducibility, which is actually more at the level of, are we sharing and are we actually embracing this as part of the research enterprise? And for the scope of the project, it actually meant we could do less, right? With the resources we had, what we set out to do, we ended up doing less because of these challenges. However, we did finish plenty. And the reason these challenges are important is what we found. And here I'm going to tie it back to another project in psychology that we did, very similar to this. We published this earlier. And these are these kind of two comparisons side by side, saying when we did replications in both of these two different fields, collecting new data, analyzing it the same way to see if we can get similar results, we see a very different contrast in what we would hope for, right? So instead of everything being identical, not to suggest everything should be perfect, we see that the replications tend to be not as significant or in the same direction as the original findings, sometimes even in the opposite direction. And more importantly, I think the size of the effects happen to be much smaller. In cancer biology, in my field, 85% smaller on average compared to the original. It's a huge difference. But even in psychology, it was half smaller than the original. So it suggests that the evidence, what we're observing and communicating each other, is not holding up quite the way that we were hoping for. So what are we going to do about this? There's a lot of things to do. And I'm going to put it in the context of even more data for a second, which is this is not unique to these projects, right? If we look across in psychology, for example, across systematic and multi-site replications, including the one I showed you, we see a similar trend, right? Weaker evidence in the replications compared to the original. So, and these graphs, these are just different projects collecting information. The zero would be identical between the original and the replication, right? The first finding and somebody trying to redo that finding. And what you see is that it tends to be weaker overall, not entirely, but you see a lot more down below that mark. So what can we do? And there's a project I want to highlight real quick in the last couple minutes, which is good practice. Doing confirmatory pre-registration and building in replication as part of the process. So this is a study I'm going to highlight real fast on my last slide, which is if you build in these processes of actually having confirmatory research like I was showing you in the cancer bio and doing self-replication, independent replication, you can actually lead to what we're hunting for, which is finding results that center around the zero that can be replicable when you do it one more time. I will stop there and pass to my colleagues to continue the conversation.
Wonderful. Thank you very much, Tim, for that. And we'll come back to many of these concepts. I'll now hand the mic over to Benjamin Haibe-Kains. He is an associate professor at the University of Toronto in the Department of Medical Biophysics. He also holds the Canada Research Chair in Computational Pharmacogenomics. He's a senior scientist at the Princess Margaret Cancer Center and also the scientific director for Cancer Digital Intelligence. And he has a lot of great thoughts on the topic of reproducibility in his domain. So I'll hand it over to Benjamin now.
Thank you very much, Rene, but I'm not able to share my screen, I think. Yeah, I don't see the option. So maybe you should switch to the third panelist, and hopefully they're going to be able to share to fix that issue.
Yes, and I'm not quite sure how to change that, but I'll figure it out while Christopher Brooks goes. Chris, would you be ready to go now? I think that it's a yes. So Chris, thank you for jumping in. Chris Brooks is an assistant professor of information at the School of Information at Michigan. He has, with some of his collaborators, thought very deeply about open science and especially reproducibility in the context of learning analytics and educational data mining. One great example of that is his project on Morph that I assume he will be talking about. With that, I'll hand it over to Chris and figure out how to get Ben online.
Thanks, Rene. Yeah, so what you're about to hear is actually going to resonate very well from what Tim just showed you, but in the sphere of education. I do a lot of learning analytics and educational data mining, but I do want you to know that it's not just about AI and data mining and machine learning. That doesn't change all of this. It makes some things easier to demonstrate and test, but this is actually a problem that goes across all of educational sciences. And so I want to share with you kind of 3 different dimensions of this phenomena that we've observed over the last, probably 7 years. Challenges in trying to replicate or reproduce or understand other people's work, what we've done to deal with that by building a platform, and then how the state of the field in education is changing to address these and needs to change. And of course, I have many great collaborators who I list there, and of course, many more. But before I tell you my woes, I want to tell you, like, why do we need this in education? And I just wanted to share a couple of things that are common in educational research that will make other people sometimes shudder, but actually exist in many other pieces of work as well. When we do educational research, often we're collecting convenient data. There's this great paper, The Weirdest People in the World, about some of the challenges that psychology faces in having a diverse group. In education, though, it's often even harder. We often have doing tests or experiments when we're doing experiments in our own courses because we're the instructor. And so we can have this instructor effect. We, of course, might only do this in 1 or 2 courses, so there's a lack of diversity, whether it be the population or the subject matter. And of course, we have this inability to share sensitive data. In the US, the data is often FERPA protected, and so we feel that means we can't share that. Another challenge, though, that comes in is when we're doing predictive modeling in particular, we're often coming up with our own features and thinking about our own dimensions of the data. And there's a lack of a tie-in to theory. And so there's idealized a loop between theory and data building. Theory leads us to generate some experiments, which give us some data, which allows us to better articulate theory. But that loop rarely actually happens. It's often theories stand for a long time before they just kind of fade and new theories come out, as opposed to these loops of data. And I think part of that is a replication issue. And sometimes we overtrain to hidden pedagogy. And so we run something in one of our courses or a course that we're close to and don't realize how important the pedagogical stance that we're taking is to the actual experiment. So the Society for Learning Analytics Research recently came out with a strategic plan about 1.5 years ago, and one of the pieces of this was to recognize the importance of open, accessible, reproducible, repeatable, and replicable data and analyses approaches, and to come up with a plan for building that within that scholarly society. So I want to share some of my examples in trying to do this. So replication challenges. We took this paper on the right and we tried, it was an early example of MOOC prediction models, made an innovative claim. They used a system that's not really known for MOOCs, Canvas. We use that often in higher ed. And we tried to replicate this. It was well cited. It was cited by about 169 people, which is pretty solid in Google Scholar. And actually, that's not quite true. That's when I last gave a presentation with this work in it about 1.5 years ago. So its citations have increased by about 100. It's been cited by almost 300 times now. The problem is it doesn't replicate well, and the nuance, there's always nuance to that. It's hard to determine if it replicates. No source code or data was provided by the author. The terms in the paper were ambiguous. So they talked about a social network degree. That's meaningful, but not meaningful enough to replicate on. How is that network being built, that social network? What did they mean by social network as far as the discussion forums? All the parameters for the models weren't reported on, so we don't know what to set those parameters, and they use Bayesian models. And there was no response to repeated emails for clarity. So we did the best we could, and we shared our code for a replication. We put it up on GitHub when we published our paper. And our results were that we found that there was actually 2 of the 6 comparisons that they made replicated statistically significantly at this P05 level. But in the remaining 4 comparisons, the opposite results replicated significantly. And I think that that's very concerning. Of course, this wasn't just the one piece of work we looked at. This was another piece of work we tried to replicate. As you can see, I'm doing a lot of predictive models in student dropout in MOOCs. Also highly cited, 135 citations at the time. In this case, though, the authors were very eager, but they didn't have their code anymore. And on top of that, the data science library landscape moves so fast, especially with deep learning, that was the context for this one, that the library they used didn't exist anymore. So we did our best effort to try and replicate this and release that openly as well, but it's a shadow of what they actually published on. And there's a huge question of like, what can we actually build? What generalizable knowledge comes out of this if we can't, even with the author's help, go back and replicate that? This led us to think more critically about how we can do these kinds of this kind of work. And so one of the platforms that we've built over the years for this is called Morph, the MOOC replication framework. It's very specific to that context. The idea here is because we can't share data, we have this run against replication. So you can provide your code into the platform as a service, and it will run it against the data and report to you aggregate results. We made this openly available. Because of the sensitivity of the data, you still had to work with us, but the source code for the platform was open. But it was all done on the margins. There was no stream of funding for this. And if you've ever seen a call for replication in education, you can let me know. I'll be honest, that actually, the first call that I've seen that specifically came out with this was last year. The IES really pulled out replication of findings as a need. And so that's been a huge win because 5 years ago, this didn't exist at all. So I wanted to just end with a few statements on the state of the scholarly practice as far as replication. And I'm very much embedded in the learning analytics community, the Kai community, the educational data mining community, the AI ed communities. These are what I would call my home communities. So these statements here are true much more often than they should be. Of course, not always. So in general, scholars don't share data, analyses, code, or code books. At best, you get the on request. That'll be done. Scholars also tend to believe that open science means qualitative researchers shouldn't, or can't participate. And I can't underline how much I disagree with this. Even code books as an example, or sample code to go with code books for qualitative research, I think is important and often not shared. Scholars tend to indicate that the data, the instrument, et cetera, is available on request, then they don't provide it or don't provide it freely. The question of freely is an interesting one. By here, I don't mean cost. Here, I mean only under NDAs, for instance, which creates a kind of contractual problem when you're doing work on that. Scholars generally fear replication, and that culture of fear is a hard thing. How do you put your work out there in a world of retraction watch? And that's a challenge that I don't think we've solved in a broader across different areas, and I hope we'll have some time to discuss. And in general, replication is not a funded piece, and it's not accepted as Tim mentioned as part of those incentives. So I think we need to start a culture of replication inside of the educational or learning sciences. And so these are the things I think we should start doing. PhD students should be doing replications as part of their doctoral studies. That should be the first thing that they have to sit down and do. How much better would it be? How can you not, learn from another scholar's approach by actually trying to do their study? I did this in, grade 10 physics with the Millikan oil drops, right? We should be doing that with our own scholarly work. Venues should privilege submissions that provide sufficient details for replication, and that can be done in different ways. We need to bring back letters to the editor to come back to our scholarly proceedings so that we can talk about when things aren't replicating and what we need to do, as opposed to every paper just stands on its own. And we need to develop norms and exceptions to those norms across and throughout the sub areas of educational research, and tools, of course, to build those. I've always loved this proverb. Decendo discimus, by teaching we learn. Doing a replication makes you think very critically about a paper, about a piece of work, about an experiment. And I really think that that should be part of what we have as our base practice.
Thank you so much, Chris. And thank you for jumping in and these very actionable steps for building a culture of more transparent science, replicability, reproducibility in the context of learning analytics and beyond. With that, I'll now invite our final speaker, Benjamin, to present.
Thank you very much. Sorry for the technical difficulties we had earlier. I'm trying to go backward. Okay, so today I'll present a little bit about reproducibility in my field, which is AI in medicine. And actually, I'll argue that the path to transparency and reproducibility is not so hard. So as the other speakers already mentioned, we really don't want to build on a miracle. This is the opposite of science. We're supposed to be very precise about what we do and how we've done things. Science is more about the process of discovery than the discovery itself very often. And so there is definitely a reproducibility crisis across different fields, and machine learning and artificial intelligence, whether it's in medicine or other fields, it's actually no different. It's actually probably worse in many aspects, and you can see different reports over the years showing that especially in machine learning and AI, there is definitely also a reproducibility crisis. And so I'll define a few terms here. So replication in my book, it's about confirming the scientific claims by completely independent investigation. So you may be using a different data set, different analytical approaches, or different patient population in my field. Reproducibility is a much lower bar. It's trying to recreate the results from the same data or samples or analytical techniques. And from a computational perspective, it's actually running the same computer code on the same data to obtain the same results. So unless you're using a non-deterministic quantum computer, it should be relatively easy, in theory, to reproduce any piece of results if you have access to the code and the data. So it should be easy peasy. But it's not really. Even if you very carefully describe your procedures, you share your data and code, it might still sometimes be very hard to reproduce results, and so it still takes a lot of efforts to reproduce a study, even if the authors shared a lot of the components. And so, because data analysis is becoming so complex, we're not really doing a t-test by hand anymore, and we sometimes generate terabytes of data. So we need a higher level of transparency. We need the results to be robust, meaning that the impact of some parameters needs to be, the investigators need to be able to investigate their impact on the final, let's say, model predictions, for instance. And maybe as importantly, we need to be able to reuse what others have done for our own research. That's how we're going to move forward much faster and help science to develop at a greater pace. But reusability is a very high bar. It means that you have organized all your research outputs so well that somebody else can reuse them in potentially different contexts. So here's a pipeline for a typical machine learning and AI study. You start with your raw data, you do the quality control and pre-processing, then you get this new version of the data that is clean, that's ready for analysis. You do, let's say, you train a deep learning model, or it could be as simple as a linear regression. You get that final model, and then you have to validate it on completely independent data, and you validate the model that way. So in this pipeline, you have actually generated quite a bit of data, not only the raw data, but also the clean analysis-ready data. You have a lot of code for QC pre-processing, to train the model, to make the prediction with that final model. Then you have the model itself. If you think of a deep neural network, it's the architecture, the weights, for instance. And something that's often overlooked is you have to also specify the full software environment. If you don't say exactly which software libraries, which operating system you're using, then it becomes much harder to reproduce, to run the code on the data, basically. And it's not a technical issue. We have technologies to help you share all those aspects of your study very, very easily. If you want to share data and it's public and small size data, you can use Zenodo and Dryad, Fixture, Harvard Dataverse, for instance. So they give you a digital object identifier, very easy to trace back. If you have private or sensitive data, you can use multiple databases. In my field of sequencing or imaging, medical imaging, there are databases where you can put your sensitive data. They're protected. People have to apply, sometimes request access to the data through a data access committee. So the level of protection for those data is actually very high. Sharing computer code, that's a no-brainer, just text, super easy. You have multiple versioning system you could use. Sharing the software environment is something that is still not mainstream. Even so, there are great platforms out there to help you create virtual machines or Docker containers where you can actually specify every single aspect of your software environment, such as CodeOcean, Gigantom, or Docker Hub. Sharing the computational models, very often it's not being shared, but if you want to let other scientists to reuse what you've built, to reuse those, let's say, predictive models, then you can share those models directly. And even if they're sensitive, if they may divulgate some information about your initial data set, you can also share them the same way you use the same system you use to share the data, which is through a data behind a data access committee, for instance. And then the analysis results, all the intermediate results, if you can share that as well, it will really help people understand if they run the code on the code correctly on the correct data. And so if you're interested in all those technologies, we've published that letter to the editor in 2020, describing a little bit, or how those technologies could have been used in a specific study I'll discuss very briefly. So if you share all those components, it becomes trivial for somebody to reproduce your work. If you have the Docker container, you can start modifying the code, click on rerunning the code. It should work by construction because it worked the first time and you specified everything. It's really easy for the community to build upon your study. If you don't share any of this, which is unfortunately often the case, then I would argue that this is not really a scientific paper anymore. It's more like a commercial advertisement. And there's this great quote from John Claerbout about the fact that in computational science, the actual scholarship is the full software environment, code, and data that produce the results, not the result itself. And so why this is important is because many very high impact papers actually are completely irreproducible. And I'll take that example from Google DeepMind, where they had this great study with a lot of samples, super sophisticated deep neural network, seems to perform beautifully well, game changer. You read that paper, you get very excited and say, oh, how am I able to kind of use that scientific advance for the best of mankind, let's say. And then you arrive to that section where they basically say, a lot of the code is about internal tooling, is very specific to our own infrastructure and hardware, and therefore we're not going to be able to release it. But all the implementation is described in sufficient detail. So if you're smart enough, you'll figure it out. And we have used a lot of open source software, some that Google actually developed themselves. So you have all the pieces, you can figure it out. And obviously this is not the right way to do so. There were obviously many details they didn't share in their paper. In our response, we actually highlighted those missing details. They had to correct their paper. But the bottom line is, without the code, you cannot really do much. And so they replied to us with some very good argument about the fact that they don't own the data. So obviously they cannot share the data directly, but there is a process to access the data, which we never argued against. It's annoying in biology, in medicine, that many of those data are sensitive, but that's how it is. So there's a process for that. Where we started to kind of disagree is the fact that some part of the code maybe they claim is of scant scientific value. I would argue that if you share a piece of code, unless it's in machine language, there is probably always something to learn, even if you don't have access to exactly the same infrastructure. So I would always encourage people to share, even if it's not easy to reuse. Strongly disagree that textual description is enough for reproduction. That is just a lie. The code is way more complex than any text can ever describe it. And then they argue that they cannot share the model itself because it could be considered a medical device and that it could be misused. So there are, ethical concerns about that. And the unrestricted access to such technology may place the patient, providers, and developers at risk. So they basically argue that their model cannot be shared because it's dangerous. They further say that, and that's probably the real reason, is that they cannot share it because they need, they're probably going to commercialize it and generate money out of it. So obviously they want to keep it a secret. And they also assume or make the assumption that their model could reveal some properties of the training set. And so all those arguments could easily be solved by sharing the models and the code behind a data access committee. So you don't allow the whole public to use it, but you can allow researchers to take a peek. After all, it's a scientific publication in Nature. It's meant for scientists to be read and meant for scientists. So they should definitely have a higher level of transparency. But obviously, they didn't release anything new. No code, no model. And so that was kind of a disappointing example, but that's very often the case in high impact publications. So it should not come as a surprise. We also had an interesting activity about student-led reproducibility challenge, where students from engineering, social sciences, and life sciences came together. They picked a paper important in their respective field, and they formed teams and they discussed their results in a one-day conference. And surprisingly, all teams faced major issue in reproducing their study. Always lack of data, badly formatted data, lack of code, or code would not run. Which was kind of interesting is that depending on the field, there were specific issues. And in social sciences or engineering, for instance, they often use software that are proprietary, whether it's MATLAB, SAS, which is not the case in my field, where we use Python and R most of the time, that are completely open source. So they also had issue with licensing, which was pretty specific to their own field and not really life sciences. So in conclusion, we've learned a lot about reproducibility. Yeah, you really have to put it at the center of your lab's modus operandi for it to work, make it mandatory, no leeway, and you have to resist the pressure. We're always in a hurry to publish. Competition is tough, but editors and reviewers really appreciate transparency and reproducibility nowadays, so it could really put you at an advantage when you submit your next study for publication. And then knowing that you're going to share all those components really kind of force you to do the best research you can, because all your peers is gonna look at your code and your data. This virtualization building of containers makes it really easy also to not only to reproduce study, let other people to reproduce it, but also to collaborate, because we all use the same software environment. But at the end of the day, the incentive, at least for me, is that sharing your research output, making your study reproducible, really increases impact. And it creates a lot of opportunities for new collaborations. And it's not because you do open science and you make yourself reproducible that it does prevent commercialization. It's a long discussion, but there are ways to still generate revenue if that's what you want to do based on open science. And being open doesn't mean you're right, but it means that you can go back, fix, you can let people scrutinize and help you improve your study. So with that, thank you. And I really hope that after the discussion, people will make their research more reproducible. Thank you.
Wonderful. Thank you, Ben, and all other panelists. You may turn on your video so we all appear. I also love the IKEA diagram at the end of that talk. I think it's a very clever visualization. There's one comment from Ryan Watkins in the chat pointing out the importance of preprint servers and as another way of driving transparency in science and maybe reducing some lag in what happens. But there's a question that I want to pose to you, and I think it relates well to some of the challenges that you've just outlined, Benjamin, but also Chris, in the challenges that come up when you try and make the work reproducible, which is specifically about sharing the data. And in most countries, there is some form of an IRB, an institutional review board, or an ethics review that looks at the plan for a study, how the data will be handled, what will be confidential, what level of privacy will be applied. And that usually asks, are you planning to share the data with anybody else, right? And this needs to be disclosed prior. And Danielle McNamara points out that sometimes saying in advance that you're planning to share it can introduce delays. Is that something that you've experienced? And what thoughts do you have on the kinds of steps, including the IRB, that need to be done in preparation so that once you get to the point in time when you want to publish the work, you are able to share the kind of information that you want to share? I'll start with that question with Ben, and then hand it over to Chris and Tim to address more.
Yeah, that's in medicine, it's a very relevant question, obviously. I don't think it's easy to redistribute data you got access to. It's 99.999% of the time it's impossible. They will not accept it. However, in your publication, you have to describe exactly the process to access those data so that they can be a review next time somebody else wants to access the data. It's painful, but unfortunately in medicine, there are no really workaround. And it's going to get harder as institutions are adopting more of a federated learning approach, where they basically say none of the data from my institution will ever leave my local infrastructure. So you're going to have to send the algorithm to us. So it basically moving the post. No, the complexity is not to transfer the data. The complexity is to transfer the algorithm and run it in an environment you don't fully control. So it's going to be interesting to see how it pans out in medicine.
Yeah, so maybe I can share a couple of thoughts. So in education, we don't have nearly the restrictions that we do in medicine with electronic health records, but there still are restrictions. It's still sensitive data, whether it's observed from an actual field experiment in a classroom or whether it's observed in a lab. We have to think about this and account for this. And so I thought I would share just briefly here, seeing this great question, one of the examples I gave our IRB about how and why we were sharing the data. And so I've just, it's a short couple of paragraphs, but the first thing I did was highlight why it's important, that this is a benefit to society, that is an important benefit because we don't see things replicating in education. Then I specified specifically the data I would share. And then I talked about, because this was a study where we were recruiting only 100 participants for, how I would reduce that data, the identifiability of that data for this particular study that we were going to share. And this kind of fits that pre-registration. So I, at IRB time was saying my intention is to share as broadly as possible because it's important. And here's how I'm going to maintain privacy and reduce that based on the people who actually come to our study, by essentially rounding some of the numbers so that you can't identify individuals. And then the last part was, where am I going to share that from? And in this case, it was in the OSF. Now, that's just one example. It really does change depending on where your study is. But I will say that transparency isn't just about data. So there's a bunch of myths of open science, I would say, and they're not really myths. They all have some truism to them. But one is that it's all about open data. And so only the quants who can share their data are going to be able to publish anymore. But it's not. Even sharing code books, sharing analyses, sharing your parameters for your models, none of these things are sensitive in any reasonable level. So I think it's important for us to move the conversation beyond sharing data to being transparent with our research and making reproducible research.
I'll just add, that was, I agree with Chris, that was excellent. And I definitely want to echo the transparency piece. Saying why you can't share is very valuable, even if you can't share the data. I think being silent is the problem, and it's a low-hanging fruit. I'm going to share one resource, though, that is very useful. I found it very useful. We've done a ton of replication projects. I can tell you from experience doing it all over the globe, or at least working with researchers all over the globe, they vary a lot. Your institution is going to be unique to you, so talk with them. But I see PSR has some great pointers that I think in terms of putting it into your consent. That's a big piece of the puzzle. So this one gives you a bunch of different languages to pick from. So just another resource to use as you keep moving on this.
That's great. Thank you for sharing that. I've got another question, Tim, for you, which is, the topic of this panel is reproducibility in AI. And I know that a lot of the efforts of the Center for Open Science started with more traditional experimental studies and looking into how to get more transparency out there, how to use tools like pre-commitments in order to have more robust estimates of effect sizes down the line. What are you seeing in terms of efforts right now that are specific about AI and predictive modeling and the kinds of studies that both Chris and Benjamin addressed?
Yeah, I'm just as curious for that answer as well, so I don't really have a good one for you. We've had a couple work that we've done with DARPA-funded projects trying to get into this. So very interested in like model cards, for example. We've had a couple things trying to figure out how to translate these concepts of pre-registration over to this domain. It obviously starts to get a little bit more complex. That's some of the things that we've looked at. I think some of the big challenges we've had were raised before, which is just trying to think a little bit about the equity piece of it. I know that especially as you get to like large processing environments, it can get a little trickier for someone to run it. But all our conversations keep pushing back to being transparent with what you can do. And I think the big one that we keep seeing is the metadata itself is of high value as well. But I'd actually be curious to hear from the other panelists what you guys are thinking, because this is a rich topic for us.
Yeah, if I may go next. So in the field of AI specifically, NeurIPS, the biggest conference in the field, is actually implementing a track where you have to make your study reproducible and the community can actually try and reproduce it. So I think it's been created and led by Joël Papineau at McGill University. And so they're doing some really great stuff there. And I would like to also emphasize Nature Machine Intelligence is doing this great initiative about reusability reports, where you're going there, you try to reproduce it, but you also try to package the software in a way that it's easy for the people to reuse. So it's kind of going a step further than the replicability. And then you have probably as many standards about what an AI model should be as there is AI models, but there have been a lot of checklists published recently about what you should really share to fully disclose what a AI pipeline, AI model is doing, and also what you should and should not do. And it's very often about making sure there is no overfitting when you design your predictive model. So there's a lot of activity, but the adoption is still extremely low. Like, I think NeurIPS is really kind of trying to push the envelope there, but the common researchers, if you look at any AI paper in any field, the probability that they're going to follow the checklist or share what they should share is close to zero at this stage.
So when we translate this into education and predictive models in education, I would say that NeurIPS is far, far ahead of what our practice is. And we all care about bias and equity in education, and replication of results is how we're going to be able to identify when people are overfitting. Overfitting is not just a machine learning problem. It's essentially us looking at one or small class and coming up with a whole bunch of generalizations for it, and then having that as sort of educational theory for decades. This is not good. And so I actually think replication is the answer to helping us actually identify generalizable theories in education, which we sorely sorely need. There is a huge gap, though, in the communities I'm in. Docker is not a well-known word, right? I mean, I'm a computer scientist by background, so this is part of my language, but we don't have one-click tooling yet to allow for this. However, we're getting better and constantly getting better. And when we start seeing the default RStudio or Jupyter development environment have that one-click, like put traces on and stop traces and then package that and give me a DOI, we're not that far away from this. So we need to keep working towards that, I think, for the education community and other social sciences.
So this raises a really important question. I think all of you have touched on aspects of this, but I want to get sort of the what you think is would be the most effective policy incentive to add, and that could be at different sort of different venues. You know, whether it's the journal itself, whether it's something within the PhD program. Clearly, there are tools, as you know, many of you have mentioned that are available. But they're often not used. And so the question is, why is that? Where do the incentives not align for it to be worthwhile, important enough for people to use them in order to get credit for using them? So I wonder if you could wave a magic wand and you know, change a policy in one place. What would it be, and where would it be? Where do you think is the highest impact, sort of lowest hanging fruit that that we could pick in order to change practice? Tim, why don't you go first?
Oof, lowest fruit. Okay, there's a lot there. You gave us a loaded question. So I think one of probably the easiest things to implement, not easiest, but requires probably the least one, is to try to take advantage of the environments that already exist at institutions in training. So basically we already have our graduate programs built around, I think, a lot of practices to kind of build communities. And what we probably need to do is infuse more of these types of concepts that we're talking about into it to kind of create that change over time. So take like even pre-registration, right? Like we do qualifying exams in our graduate education. That's not the exact same thing, but it's getting these concepts closer and closer. So I think that would be one of the easiest things to do, just because the infrastructure exists. I don't think it's going to have the biggest change, because I think the other part that I pick is funders. I think the funders need to actually be able to change to support. They hold the money. That's going to change the behaviors the fastest, but it's also the hardest thing to do. So I'm going to give you two answers, one that I think you can do now and one that's going to be much harder.
I'm just going to jump in and pick up, because I think my answer is kind of similar to Tim's. The thing that we can do is, if you're getting a PhD in a quantitative field, you should have to do a replication, because it's going to give you deep insight into all the challenges in doing a replication and all of the ways that it doesn't quite work, or the issues that are faced. And through that, it will make your own practice as a scientist better. And I think that's something that's something very easy for us to do. And at the same time, it's very hard, because you don't get your replication published. There's very few places that you can actually do this, especially a top-ranked journal in education. Or Kai, for instance, used to have workshops specifically about replicae, and now that's less. There's a lot of novelty as a focus there. So the downside of this is that it requires all of us to do it as a community, those of us who are training graduate students. And if we don't all agree to do it, then somebody else will have n number of novel publications coming out, instead of starting with this hard slog of a replication, and it won't move us forward.
Yeah, I'll provide a bit of a pessimistic, optimistic perspective on this. I've seen that my generation and the next one are much more likely to invest and value open science than the old guard. And so I would say wait 25 years. All the leaders will retire by then. The new generation is coming up. I agree with Tim and Chris. I think education in terms of reproducibility, replicability, open science is the key to really kind of change the game. However, science is done by humans, and we all respond to certain incentives. So I think making it part of the culture. Like it should be part of your promotion package. It should be the way your peers value your work. So there are the DORA principles, a kind of a step toward this, where they recognize different kinds of contribution, not just the impact factor of the journal you publish in. So there are a lot of trends. If I could change, like with a real magic word, I would definitely change the funders, because as Tim said, they have the money, they can change even the old guards. So I would do that, but I think the real hope, the realistic hope is the new generation. We have to teach them about those concepts.
Those are all great starting points, and a lot for people in the community and people attending and watching this later to consider in their own training and the way that they inspire the next generation of students, of researchers, of scholars in the field, and and for any funders in the attendee list, also something to consider. I want to ask you one last question in the few minutes we have remaining, which is about the effects of some of the things that we've already seen. And one of the things that came out a few years ago, and I think in direct response to the work on the reproducibility crisis in psychology, was journals giving badges for different kinds of making things available. So I wanted to ask Tim, I think the Center for Open Science was part in sort of suggesting that policy. Is that an effective strategy for others to implement? What is the jury out on whether that helped in the right direction, or did that set up incentives that were not favorable?
Just to make sure I understand the question, you're asking about, like, in the Center for Open Science, in terms of the policy work that we've done in terms of trying to incentivize the change.
And the actual change that was implemented by places like Psych Science and several other journals that started highlighting this work has open data or has open materials.
Yeah, I mean, so I'll answer in a general way and then others jump in. The work that we've done, one of the approaches we had, I didn't really talk about that, is kind of looking at it across the whole system. So as much as like we've jumped at two levels of funder, and if I had to pick one, right, funder versus researcher, the approach we took and try to do in other fields as well is to do it across that whole spectrum, right? So it's not just policy to require something, it's working with journals and institutions to incentivize those behaviors. That's actually what will happen. You don't have to tell me what to do something, but if you reward me for it, I'm actually probably more inclined to do that. But also giving the tools. So everything from the tools to making those tools easy, to making them visible, so that way it becomes normative behavior, to eventually also requiring them. That's been the approach that we've taken, and it seems to have worked really well in psychology. The question now is, how do you translate that into more disciplines? Because I think if you just do one and it's disconnected from the others, it won't succeed. So we kind of needed it from the top to the bottom in terms of that whole spectrum.
Other thoughts on that?
Maybe one tidbit. I call it the hit and publish behavior. So you publish and then you run away from it. You really don't want to deal with that issue anymore. Why? Because it's much better for you to jump on the next hot question than support the study you published 5 years ago. That for me is a very troubling behavior as a scientist. But I understand that the incentives in place are rewarding the quantity over the quality of some of your papers, right? So I would be very curious to see how we can change that hit and publish behavior and start to record, monitor, and reward the scientists who can actually support their study post-publication. You convince three reviewers and an editor that this is worth publishing. That's just the beginning of the journey. And I think in some other fields, like mathematics, for instance, they're much better at this than we are. It could be the nature of their field. But in life sciences, we are really terrible at this.
I think bringing this to the field of education, the way we should tackle this is to change the discussion about what replication does for us. And it is about removing bias. It is about finding a generalization. It is about that connection between data and theory that we don't actually have, even though we like to talk about this cyclical connection. And I think that once we start framing it in that language, then reproducibility comes naturally as a potential solution or a partial solution.
on that note, I think we're at the end of our time. Thank you for the great discussion, Benjamin, Tim, and Chris. I learned a lot, and I hope our attendees did as well. There's a few questions for the resources. Remember, this is a recorded talk. It will be posted afterwards for anybody to re-review. I will collect some of the slides and materials from the chat and make sure that they are posted as well online for some posterity in case you want to look them up. But thank you again, and see you at the rest of the conference.